Hello everyone. Today's session, I'll discuss about special matrices and their properties. I'll also discuss about determinants and the Cramer's rule. After this lesson, you're expected to review the properties of special matrices and solve problems of equations or systems of equations applying the operations of matrices. Square matrices. This type of matrix is important when we solve systems of equations, and square matrices have some special properties. In the figure below, you will see the arrangement of a square matrix. The elements of the main diagonal or the centermost diagonal are those from the upper left corner to the lower right corner of the matrix. Hence, these elements are referred to as diagonal elements, or simply diagonals. If all elements except those on the diagonal are 0, the matrix is called a diagonal matrix. The two below are examples of diagonal matrices. So where you can see that the only non-zero values in those two matrices are located in the main diagonal. Hence, they are called as the diagonal matrices. If the non-zero elements of the diagonal matrix are equal to 1, the matrix is then called an identity matrix. There are several orders of an identity matrix where n refers to the number of rows and columns. The notation used for identity matrices is I sub n. Below are examples of identity matrices where we can see that the subscripts represent the size of the matrix. So in this example matrices, I3, I sub 3 or 3 have the size of matrix 3 by 3. Also with 4 and 5 where the subscript of I represents the size of the matrices. Identity matrix has a property that for any n by n matrix A, it is always true that A times I, or the matrix A multiplied by an identity matrix, is equal to, when interchanged, like the product of A times I is equal to the matrix A itself, meaning that it can be interchanged and still obtain the same product. If two rows of an identity matrix are interchanged, it is referred to as a transposition matrix. A transposition matrix can be also obtained by interchanging two columns, not only rows. Consider the identity matrix below. So we can see, here we see the identity matrix represented by I sub 4, and thus the transposition matrix P sub 1 is obtained by interchanging the second and fourth rows. So you can see in the transposition matrix P sub 1 that this matrix is obtained by interchanging the columns 2 and 4. Now let us multiply the transposition matrix P sub 1 with the matrix A. So let's consider a matrix A with these elements, and we'll multiply it with the transposition matrix P sub 1. If you look at the product matrix, the product is A, but with the same two rows interchanged. So we'll do a multiplication of these two matrices, and we can see that the product of P sub 1 times A times n is equal to the matrix A, only that the second and fourth rows are interchanged. Okay, so you can see here that the that the rows 2 and 4 are interchanged. Okay, look at this matrix A. So you can see that this that in the product matrix P sub 1 times A, the rows 2 and 4 are interchanged. Why? Because in our transposition matrix, the second and fourth rows were interchanged. Thus the product of these two matrices have the second and fourth rows interchanged as well. Now let us multiply again the two matrices P sub 1 and A, but in reverse order. In reverse order, we do multiplication in the order that A times P sub 1. What happened? The result is a matrix A but with columns interchanged. When we mean columns interchanged, let's take a look at this matrix A. So matrix A is this is the arrangement of the elements in matrix A. When we multiplied A times P sub 1, what happened is that the two columns were interchanged. What columns? The second and fourth columns were interchanged. What happened? Because as we can see here in the transposition of matrix P sub 1, these two columns, second and fourth columns, were interchanged. Therefore, in the product of the two matrices A times P sub 1, the result is just the matrix A, only the second and fourth columns were interchanged, just like what happened with the transposition matrix P sub 1. Alright, let's proceed with permutation matrix. This matrix is obtained by multiplying several transposition matrices. Another property is this symmetric matrix. This is a square matrix with pairs of elements in similar positions across the diagonal, where these elements are equal. So just like this example shown below, so we can see that the pair of elements surrounding or across the diagonals are equal. So we can see here that the elements across the diagonal, such as this y and y, are the same, just like the g and z. So these pair of elements are equal across the diagonal. The transpose of a matrix is obtained by writing the rows as columns or by writing the columns as rows. So let's take a look at this example. So we are given here a matrix of these elements. What happened when we get the transpose of the matrix A? So we have here that the arrangements of the columns 301, negative 1, 2, 1, and 4, negative 3, and 2. What happened when we obtain the transpose of this matrix? The column here, it is rewritten. The column here in this matrix A into rows in this transpose. Now the columns here became rows in this transpose. That's 301, negative 121 became row negative 121, and lastly the column 4 negative 32 became the row 4 negative 32 in its transpose. This transpose of a matrix is represented by the notation AT. This example, okay, and it has several properties as well. So for a symmetric matrix A, A is simply equal to AT. It should be noted that this is the relation, since for a symmetric matrix, the pairs of elements across the diagonal are just the same. Thus, when we obtain or we write the columns as rows and columns or columns as rows or as columns, or vice versa. There's no change in the elements. And for any matrix, the transpose of the transpose, say that the transpose of 80 is just the matrix A itself. Thus, this expression, right? Another property involving transpose of a matrix is that the transpose of two matrices multiplied, such say that the transpose of the product of matrices A and B is just equal to the product of the transpose of B and A respectively. Alright, so this is the relation when we involve multiplication of two transpose of a matrix. Alright, or even when we transpose the product of two matrices. Now, for a square matrix, we have a quantity called as trace. Trace is the sum of the elements on its main diagonal. For example, given the matrices below, the trace is equal to 7. We obtain the trace by simply adding the elements in the diagonal. So the values in the diagonal of these two matrices are 3, 2, and 2, and therefore the trace is equal to 3 plus 2 plus 2. Alright, so this is wrong. This is supposed to be 2. So 3 plus 2 plus 2, our trace is equal to 7. If all the elements above the diagonal are 0, the matrix is called lower triangular. We will see in this, in this example, we see that the matrix forms a right triangle in the lower part of the elements. Alright, so since the elements above the diagonal are 0, we can see that the non-zero elements form a right triangle in the lower part of its matrix. Hence the name lower triangular matrix. On the other hand, if all the elements below the diagonal are 0, the matrix is then called upper triangular. Below is an example of an upper triangular matrix. So we can see here, just like with the lower triangular matrix, the elements below the diagonal are 0, and thus we see here non-zero elements forming a right triangle in the upper part of the matrix. These two matrices, upper and lower triangular, are of special importance, as we will be covering more of these matrices in the next lessons, and this is important especially in solving systems of linear equations. Triangular or tridiagonal matrices are those that have non-zero elements on the diagonal and in the adjacent positions to the diagonal. So take a look at this example. So you will see non-zero elements in the main diagonal. So this is our main diagonal. All the elements here are non-zeros. And we can see in the adjacent two positions to the diagonal are also non-zero. So these elements are also non-zero. So we see here 3 diagonals that are non-zero. Hence the name of this matrix as tridiagonal. Tridiagonal matrices have also special importance in numerical methods, especially when we obtain the solutions of partial differential equations. Oftentimes, operations involving tridiagonal matrices only have non-zeros as important, and are therefore only need to be recorded. And thus, for an n by n matrix, it can be compressed into a matrix of 3 columns and n number of rows, like this example below. Okay, so this is a compressed form of a tridiagonal matrix, compressing it into a matrix of 3 columns and n rows. In solving some applied problems, it will be inevitable to encounter problems or elements that where or matrix where only a few elements are non-zeros. Thus, a matrix that matrix is called a sparse matrix, just like this example. So we can see here in this matrix that there are only few elements that are non-zeros. Thus, this is called a sparse matrix. So in the preceding lessons or preceding problems, you will encounter more about sparse matrices. Now let us consider about determinants. So this is a review of the knowledge you obtained in the lower years. So I'm pretty sure that you have encountered determinants, especially in your course Advanced Algebra. But in this course, this is of great importance, especially when we're trying to solve systems of linear equations. For a given matrix A, the determinant denoted the determinant is denoted by D, or determinant of matrix is calculated by this expression. So where the product of the elements on the minor diagonal from upper to lower left is subtracted from the product of elements on the major diagonal. So we can see here that obtaining the determinant involves getting the product of the diagonals of the main diagonal and the remaining diagonal and subtracting it from this subtracting the product of this from the product of the main diagonal. So such as the element a11 is multiplied by a12 and we subtract it with the product of a12 and a21. So yes, all right. So let's take a look a few examples of obtaining determinants. All right. So we can see here on the first example, matrix with these elements 3, 2, -1, and 2, and therefore we obtain the determinant by multiplying 3 and 2. So this is our main diagonal, and we subtract it with the product of 2 and -1, and therefore we have our determinant equals to 8. Second example, so we have these elements of the matrix A, and -1/2, 1, and get by the same procedure we get determinant as 0. Another example is this matrix A with these elements, and using the same procedure we get determinant which is 0 as well. And lastly, we have the example of this matrix -5, 3, 7, 2, and using the same procedure we obtain the determinant as -31. You observe that our examples only considered second order matrices or 2 by 2 matrices. Now let us consider a third order or 3 by 3 matrix. The determinant is represented by this expression. So we can see that the elements in the upper row are multiplied by their corresponding determinants. So what are these determinants? So for example, in getting this first term, we multiplied a11 with the determinant for a22, a23, a32, and a33, and as well as the other two terms, we obtained the terms that by multiplying A12 with these determinants and also with A13. Okay, so these determinants that we multiplied with the elements are called minors. Okay, and notice the sign. So what? Please notice these signs. So first we used a positive sign for this expression, then the next sign we use negative, and we revert back to positive sign in the third expression. So in obtaining the determinants, the sign and minus signs are used alternately. Okay, so in order to understand more about obtaining determinants for example, for this third order case, we will consider another example. Okay, but first is that this is how we obtain the expression for determinants. All right, so you can see the pattern here on how we obtain this expression. Next, for A12 is multiplied by the minor determinants below, and A13 is multiplied by this set of elements representing the determinant or the minor. Okay, so let's consider this example. So this is a 3 by 3 matrix, and we will get the determinants of this matrix. So using the expression in the previous slide, this is how we will get the determinant of this matrix. So 0.3 is multiplied by this minor, minus 0.52 is multiplied by this minor. So this is 0.5, 0.1, 1.9, or 0.5, and lastly the last term is 1 multiplied by this minor. Right. Next is, so since this expression is, we will still get the determinant here. Thus, in our next step, we will multiply 0.3 by the determinant of those minors. Alright, so 0.52 is obtained with the expression for the determinants of this minor, and as well as the last term 1 multiplied by the determinant. Now, evaluating further, we obtain that the determinant of the matrix A is negative 0.0022. Okay. The same process is used in getting the determinant of higher order matrices, such as this 4 by 4 matrix. And we'll take this example. Okay, so in getting this, by using the same procedure, we have, for example, for this 4 by 4 matrix, the corresponding minor in the first step of solving the determinant is equal to is a 3 by 3 determinant. All right, so for this we multiply by this minor. So the minor for a 4 by 4 matrix, the first minor for a 4 by 4 matrix is a 3 by 3 determinant. All right, so we change the sign for the second term, negative, positive, and negative sign, and we use it in alternately. Thus, evaluating further, we obtain the determinant for that 4 by 4 matrix as negative 146. Okay, so for those previous examples, starting from getting the determinant of a 2 by 2 matrix, please check yourself with using your pen and paper. Please check these examples. Please verify it yourself by solving those examples if the answers I had here is the same with what you have computed. Okay, so for this I will not I'll not be discussing in detail on how the matrix for this 4 by on how the determinant for this 4 by 4 matrix is obtained. So please follow the procedure and check it yourself. All right, we obtain the determinant is equal to negative 1, 4, 6. Okay, our next topic is the Cramer's rule. Okay, so Cramer's rule states that each unknown in a system of linear algebraic expressions or linear algebraic equations may be expressed as a function of two determinants with the denominator d. So what is this denominator d? Denominator d is the or d is the determinant of the matrix A, and with the numerator obtained from D by replacing the column of coefficients of the unknown in question by the constants b1, b2 up to bn. Alright, so we know that the expression or the expression for a matrix is represented by this. So ax is equal to b. So just like an example below, in order to get the unknown like x sub 1, take notice of this of the right hand side of this equation. In this numerator, this is the determinant for the matrix A. Okay, so thus it contains the elements a sub 1 to a sub 3. Okay, notice that our first the unknown that we are trying to get by this expression is x sub 1. Thus, we substitute the columns in this numerator with the values of with the values in B, right? And the numerator of this expression is the determinant of A. All right, so let's take a look at this example, which consider this. Okay, so this is a system of linear equation that we're trying to solve, and here we are trying to obtain the values of x sub 1, x sub 2, and x sub 3. All right, so we can transform those that system of equation into this form: ax equals to b. So where this matrix is the matrix A representing the coefficients, and thus these elements of this matrix is the coefficients, and thus we have x here, which is the unknown variables, and this matrix is the matrix for B. All right. Next is that for Cramer's rule, this is the procedure. This is the expression in obtaining the values of x1, x2, and x3. All right. So what we did with x1 is that in the numerator we simply replaced the column for the first column with the values of the matrix B, right? And for x2, replace the second column with the B matrix, with the elements of the B matrix, and lastly with x3, the determinant of A is replaced with the values of the matrix B. However, we take notice that the denominator is the same, which is the value of the determinant. So first is that we'll have to get the determinant of the matrix. So this is the matrix A. So we have given here the matrix A here. We obtain the determinant. So in your pen and paper, let's check yourself and solve this problem. First, getting the determinant, and here we obtain that we obtain the determinant is equal to negative 0.0022. All right, please check yourself. Please check this determinant yourself. Right, and for the unknown, since we already obtained the value of the determinant, we will get into the determination of the values of x1, x3. Okay, so for the numerator, we replaced the values of in the first column with the values of the b. This is what we have replaced. So in this numerator, we will get the determinant. Okay, so in your pen and paper, please get the determinant of the numerator and check if the determinant is for the numerator is 0.03278. Right, so you'll do this yourself and dividing it with the obtained determinant of the matrix A, negative 0.0022, we have the value of x1 is equal to negative 14.9. Next, for the variable x sub 2, we simply replace the second column with the values of the matrix B. So here we will get the determinant in the numerator. Let's check yourself and check it if the determinant is equal to 0.0649. And also we will divide it with the determinant of matrix A, and thus we have x sub 2 is equal to negative 29.5. And lastly, with x3, we replaced the third column with the values of the matrix. We obtain the determinant of the numerator as negative 0.04356. Dividing it with the determinant, we obtain the x3 is equal to 19.8. So in this problem, by using Cramer's rule, we obtain the values of x sub 1, x sub 2, and x sub 3. Okay. So Cramer's rule is almost easy to use when involving a 3x3 matrix. However, with larger order matrices or larger systems of equations, using Cramer's rule can be a little tedious or even more difficult to use, or not as fast with other methods in solving larger systems of equations. But it is most useful with the smaller systems of equation. Okay, but the concept of this Cramer's rule is of great help. Is of great help in understanding more about the concept of solving systems of equations. So as a summary of this lecture, we discuss about square matrices and its special properties. There, we discuss about diagonal, identity, transposition, permutation, lower and upper triangle matrices. We also discuss about tridiagonal and what is a sparse matrix. Subsequently, we reviewed about determinants and the procedure of obtaining it given a matrix, as well as the Cramer's rule. To wrap up this lecture, I would give credit to the author of the reference textbook used in this lesson and in this course. These books are the Numerical Methods for Engineers by Chapra and Camille, and the Applied Numerical Analysis by Gerald and McLean. So this is all for now in this lecture. See you on our next meeting and lecture. Thank you very much.